You know when you're just looking at the world and you're struck by a flash of unexpected color? Like a shimmer on a CD, or a little rainbow in a spider web, or even that weird glow around a cloud? Well, these aren't just random bits of beauty. Nope. They're actually clues to a really fundamental secret about how light works. And what's wild is they're all connected by a single amazing principle. So let's uncover it together. So I want to start with this one beautiful question. What exactly is that shimmering silvery edge you sometimes see on a cloud? I know, it sounds super poetic, right? But the answer is pure physics. And what's so cool is that the exact same principle that explains this, well, it also explains a whole bunch of other everyday light puzzles.
I mean, think about it. You have definitely seen these before. The way light breaks up into a rainbow on the back of a CD. Those almost magical colors you can spot in a spider web or a soap bubble. Heck, even that oily sheen on a wet patch of road. They all seem totally unrelated, but they're not. They're all just clues pointing to the exact same scientific secret. And today, we are going to crack the case. All right, so the key that unlocks all of these mysteries? It's got a name, diffraction. Now, I know, it sounds a little complex, but the basic idea is incredibly simple. It's all about what happens when light is forced to bend.
So what is diffraction? At its absolute core, it's just the bending or spreading of light waves. You know, the best way to picture it is to think of a wave in the ocean hitting a big rock. The wave doesn't just stop, right? It wraps around the rock and keeps going on the other side. Well, light does the exact same thing, just on a much smaller scale.
So then, why don't we see light bending around corners all the time? Well, here's the catch. This effect only becomes really noticeable when the obstacle or the opening is incredibly tiny. We're talking about the same size as the light's wavelength. It's kind of like the light wave has to squeeze through this super narrow doorway, which causes it to spread out on the other side, instead of just going straight.
Okay, so we've got a theory that light bends. But how do we know this is actually happening? Well, scientists found the proof by looking for the visual fingerprints that this bending leaves behind. And these patterns, they prove that light isn't always what it seems.
Now, what's really fascinating is what happens after the light bends. See, when all those spreading waves start to run into each other, they interfere. Sometimes they build each other up, and that creates a bright spot. Other times they cancel each other out, creating a dark spot. And the result is this really distinct pattern of light and dark. That's what we call an interference pattern.
And this is where the proof becomes just undeniable. Scientists tested this with a pretty simple setup. So when you shine light through a single tiny slit, you get a bright central bar of light that kind of fades out. But, and this is the amazing part, when you use two tiny slits right next to each other, you get this unmistakable pattern of many sharp alternating bright and dark bands. And that can only happen if the light waves from each slit are spreading out and interfering with each other.
And this is the big reveal. That interference pattern is the smoking gun. It is solid, observable proof that light doesn't just travel in a straight line like some tiny little particle. It also travels and behaves like a wave, which means it's capable of bending and spreading and interfering. So now that we kind of get the science of diffraction, let's go back to our original puzzles. How does this wave-like bending of light explain that rainbow on a CD or the silver lining on a cloud?
Let's start with the CD, okay? The shiny surface of a CD isn't actually smooth, not at all. It's covered in a spiral track of billions of microscopic pits, and these tiny little grooves, they act as what's called a diffraction grating, which is basically just a surface with thousands and thousands of tiny parallel lines that force light to bend.
Okay, so let's walk through exactly how this happens. First, regular white light from a lamp or the sun hits the disc. As that light passes over those thousands of tiny lines, it's forced to bend. That's our diffraction. But here's the magic part. Not all colors bend the same way. Red light has a longer wavelength than blue light, so it bends at a slightly different angle. The CD basically acts like a prism, separating all the colors and fanning them out into the rainbow that we see. And that final spreading of colors, that's known as dispersion.
So the rainbow on a CD is this beautiful everyday example of what's going on. But, understanding diffraction is about so much more than just solving light puzzles. It fundamentally changed how we see the universe. It proved that light has this strange dual nature. It's both a particle and a wave. And that idea, it's a cornerstone of all modern physics. All right, so let's just recap the crucial points here. 1. Diffraction is the bending of light. 2. This bending causes interference patterns.
3. Those patterns are the proof that light behaves like a wave. And 4. This single principle explains so many beautiful things we see every day. From the iridescence of a soap bubble to, yes, the silver lining of a cloud, which is really just sunlight diffracting around the tiny water droplets at the cloud's edge.
And I'll leave you with a final thought to chew on. You can easily hear someone talking around a corner, right? That means sound waves are diffracting quite a bit. But you can't see them. So based on what we've learned today, why do you think diffraction is so much more obvious for sound than it is for light? It's a great question to ponder. Thanks for tuning in.